Hello, I'm going to be doing recap video number 5, and number 5 is going to be broken up into 2 parts to make sure we get everything in. We're covering fundamental theorem of calculus in this video, and there are 2 parts to the fundamental theorem of calculus. There's part 1 and there's part 2. This first one that's listed for you is usually considered part 1, and the second part is usually considered part 2. Now, what the first one says is that if I take the integral from a to b of f of x dx, I get the net change of the antiderivative. So this is called the net change of the antiderivative. Or we might say this is the, well, we'll keep it as that. We'll say the net change of the antiderivative. Another way you might see that written is if you have the integral from a to b of f prime of x dx. And notice what this is saying, the integral of the derivative. And when you have the integral of the derivative, you end up getting, again, the net change. So the net change of the antiderivative. For part 2 says, well, what happens if I take the derivative of an integral? This is what I end up getting when I take the integral of the derivative. That's part 1. But part 2, if I take the derivative of the integral, take a look at just this part. If I keep the d dx in front, I end up getting the antiderivative of little f of t, which is big F of t. And I'm going to evaluate that from a to x. And that's going to be d dx of, again, fundamental theorem says the net change of the antiderivative, so I'll plug in x and a and subtract. So big F of x minus big F of a. And that's what my antiderivative is. And then when I take the derivative with respect to x, the derivative of big F is little f. And the derivative of a constant, 0. And that's how we find out that the derivative of the integral is really just where we started, f of x. And I kind of wrote over that. Now here's this other part, and this part is kind of important, well actually very important, because you should wonder, well, what happens if we don't have an x for one of the limits of integration? What instead if we have a function like g of x, or g of x could be anything like x squared or whichever. So let's see what happens one more time if I take the fundamental theorem of calculus part 1 and apply it here. The antiderivative little f would be big F of t, and I'm evaluating from a to g of x. And the only reason I'm doing this is I want you guys just to be able to see where these quote-unquote formulas are coming from. When I do the fundamental theorem of calculus here, I have the net change of the antiderivative, so I have big F of g of x minus big F of a. And now I'm going to take the derivative of that with respect to x, and the derivative of big F is little f again. And it looks like I'm going to have a chain rule here. I'll keep the inside function and then multiply that factor by g prime. And the derivative of a constant is just 0. So these are 2 really important ideas, how to take the derivative of an integral and the integral of a derivative. It's the whole point of what the fundamental theorem of calculus does. It unites the derivative and the integral and kind of undoes them in a way in an inverse operation. The last thing I want to show you is something that I think that I usually find helpful to show. And that is, what if we have a function in the top and the bottom of the integral and we're taking the derivative? So let's say we have h of x here and g of x. I'm going to skip the work because you shouldn't need to actually find the antiderivative. So I'm just going to write that down. No need to find the antiderivative, because when you're going to take the derivative of the antiderivative, you end up back where you started again. So no need to find the antiderivative. Instead, we'll use our shortcut, if you didn't realize it already, although you've already been taught it, I imagine. So the shortcut is, let's see here. I would take g of x, plug it into t. So the derivative of this integral is going to be f of g of x. But remember, when I take that derivative, I'm going to have to multiply times the derivative of that limit of integration, so times g prime of x. and then subtract the lower part, minus f of h of x times h prime of x. Make sure you re-watch any part that you need, but please know the fundamental theorem of calculus, both parts, like the back of your hand. Next. Okay, so a function defined by an integral. I think you've seen these a lot by now. Basically what we're going to have is we're going to have g of x be equal to some integral a to the x of f of t dt. This function would be f of t, and here's a, and here's x. And what it's saying is that if I want g of, let's say, 2. So if I want g of 2, and I'm going to call this value actually 1, just to make it a little bit more precise. If I want to know what the actual y value is when x is equal to 2 for the g function, and I notice that the g function is dependent on the integral of f function, what I'm going to do is I'm going to say g of 2 is equal to the integral from 1 to 2 of f of t dt, and here is 2, and what I would do is I would fill all this area in. So all of this area is, whatever I found that to be, would be equal to g of 2. And I could do that for any function, and that's the kind of cool part about this. So if I wanted to, I could do this for any value. So if I wanted, instead of g of 2, I wanted g of 5, then all I would do is I would go all the way out to g of 5 and find that area. And that area accumulated would be the value of g of 5. And this again works, this idea of accumulating area to find a y value on a different function is true if you go to the right and if you go to the left. It would still be the same thing. You would just accumulate how much area, and that area based on your equation would be the y value for that function, for the function defined by an integral. Practice these types of problems. They always appear in FRQs. So, always in FRQs. And when I say it's always in FRQs, I'm talking about g of x, a function being defined by an integral. Okay, we got 2 word problems to take care of, and that will actually take us the rest of the 7.5 minutes. So here's how it's going to work. I want you to go and pause the video. I'm going to talk about it once you're done. Then you're going to pause the video again, and you're going to go in and try the problem on your own. Please pause the video now to go ahead and read the problem first, and then resume when you're ready. Okay, so the key things that I want you to realize here are going to be some keywords. A company is offering a company for money off at a popular chain restaurant in the month of June, and they tell us the rate. So that means a of t, even though it looks like original function, is actually a first derivative. And that is worthy of writing down anytime you see something like that. So this part is the first derivative. First derivative. And actually the same thing is going to be true for m of t, because m of t also says that there's a rate. So m of t is also a first derivative. Notice also we have 2 rates. We have a rate at which that's accumulating an amount of people, and a rate that is subtracting an amount of people. That's also accumulating, but one's being added, one's being subtracted. And the AP test usually likes these type of problems, having 2 different functions in there. Another thing that I want you to highlight here is that both A and T are measured in people per day. That's important. And we're only looking from 0 to 30. And the most important part of all of this, and I know I said a lot of this is important, is that time t equals 0, 100 surveys have already been taken. And this, my friends, is called an initial condition. You're going to need that at some point. I don't know when yet, but you're going to definitely need that. So I want you to go and pause the video, try all this on your own, and then resume when you're ready. Okay, here's your answers. Let's see if you did it right. First of all, I also want to note that whenever you have 2 functions, I'll usually put y1 and y2 just so I know which function is going to be in the calculator. And then here are your answers. Part A, there's that initial conditioner. You need to add in that 100 to be able to find out how many total surveys were answered by June 15th. So we'll have the integral, 1,241 people is your answer. I'm writing out my answers here in complete sentences just so that you are aware of what the meaning of that number is, because the AP test is going to frequently ask you to interpret what that number is represents. For part B, to find out how much total cost, I took that value in A. So I took this entire value, 1,241, and I multiplied that times 10, but I also called this B, so I didn't have to rewrite it again. I also did plus $5 times, and I accumulated however many people actually answered the survey after June 15th. And I could have written Y1 here or AFT, but I'm not writing the function over and over again. I'm using the function names. That was 13,677. For part C, so they just wanted me to plug in f of 15, and that got me 420. And then the second thing is, and this was a calculator part, the second thing is they wanted me to tell me, they wanted me to say what that actually represents. And 420 represents the number of people who answered surveys by June 15th, but did not receive coupons. And that's what that means when we take A of X, which is the number of people that answer their surveys, but subtract off the people that received coupons. So a whole bunch of people that answered surveys, there are a subset of people that got coupons. That means there's also a portion that did not get coupons. And that's what this value represents. Please also note, by June 15th, we are looking at an instantaneous rate. So who answered surveys by... Okay, next. For D, here's your answer. Again, we're taking a rate, subtracting a rate, because that's what f prime of t is finding. And our value is negative 33.417, and in green is what that represents. Please pause the video if you need to read it a little bit more, but we're going to go ahead and move on. Jack is climbing down a vertical beanstalk. I'm going to just highlight a few things. I know you haven't read the problem yet, but you're welcome to pause now and try to read it. We've got a rate again. We've got another rate, and there's two rates going on. And since they're both in different places of the beanstalk at different times, that means one subtracting another is going to be the key idea here. Please pause the video to try the problem on your own. Resume when you're ready. How far down does Jack climb in 15 minutes? That's an integral. If we know that he's climbing in feet per minute, then in order to find out the feet, take the integral from 0 to 15, you get 690.563 feet. Please make sure you're using 3 decimal places. For part B, the distance between Jack and the giant. So I have two equations here. I have 1600 minus the integral. I have to use that 1600 because that's his initial position, and I have to see how far down he went after 15 minutes had elapsed, and that was 909 feet total. So he is 909 feet above ground right now at time t equals 15. The giant similarly is going to be 1,705 feet above ground at this time. So subtracting those two, I got 796 feet above ground. That's the distance between them, actually. To find whether this distance is increasing or decreasing, I'm going to use their rates and see if that rate value is positive or negative. I plugged in 15 for J and G and subtracted, and I found out that value is positive, so the distance is increasing between the giant and Jack. For part C, the time that it's a maximum, I take the difference of their rates equal to 0. I solve for t and get 29.664. And then I find that the difference of those rates is positive when t is less than 29.664, but greater than 0. And I find that that difference of rates is negative when t is greater than that t value, but less than an hour. Therefore, my maximum is going to happen at 29.664. For D, 1600 equals the integral from 0 to k of j of t. And finally, for part E, does the giant reach the bottom of the beanstalk? I evaluated the entire hour to see how much he actually went and subtracted 2,000 from it. He ends up being 170 feet above ground when we get to an hour, so he's not reaching the ground at all. Thanks for watching, guys.